Good afternoon, and thank you for joining us this afternoon for today's ATA educational webinar, Acoustic Simulation and Characterization in the Aerospace Industry with Simcenter 3D. I'm here today with our guest speakers, Dr. Korjan Kukakoskun and Dr. Bert van Genechten, both from Siemens and experts in acoustic simulation and measurement. Before we get started with the webinar proper, a few housekeeping things. We welcome your questions. So if you want to ask any questions, you can put them either into the Q&A panel or the chat panel, and we'll get them. We will most likely push all of the Q&A to the end of today's session so that the presenters may be free to respond in full. If it's a very simple question, then we may be able to answer it on the chat. Our sponsor for today's webinar, of course, is ATA Engineering. So I'll introduce a little bit about ATA Engineering and also the Simcenter 3D product portfolio, of which this acoustic simulation software is just one important piece. So ATA Engineering is an employee-owned small business with a full-time staff of almost 200. Our headquarters is located in San Diego, California. We have a very experienced staff of engineers who have worked on a wide variety of projects for government and industry. Our specialty is providing high-value engineering services to help solve our customers' toughest product design challenges. Our principal industries that we serve are aerospace, space and aerospace. So aircraft, launch vehicles, satellites, liquid rocket propulsion, etc. Also, robotics and controls. We have a very interesting practice in themed entertainment. Think roller coasters, animatronic figures, that sort of thing. We work in the defense field and are a classified U.S. government defense contractor. We also work in industrial and mining equipment, consumer products, and other fields, wherever our customers need high-value engineering services. We provide these services from our offices nationwide, starting with our headquarters in San Diego, but with branch offices in Los Angeles, the San Francisco Bay Area, Denver, Albuquerque, Huntsville, Alabama, and Herndon, Virginia. And coming soon, our Northeast Regional Office in Boston, and a new office that we are going to be starting up in Madison, Wisconsin. Our specialty is design, analysis, and test, but we are also a Siemens Platinum level solution partner for Siemens software. As a value-added reseller for Siemens, we provide licensing and support for Siemens NX, Nastran, VMAP, Star CCM+, Simcenter 1D, Simcenter 3D, Teamcenter, and many others. We are also a Siemens preferred training provider, and in fact, all of the training materials for Siemens Nastran FEA solver are actually written under contract by ATA. So when you come to an ATA training class on Nastran, you are quite literally being trained by the person who wrote the book. For more information on the various products that we sell and support from Siemens, you can visit us at our website. Now, for just a few slides on Simcenter 3D, for those that are not familiar with it, Simcenter 3D is not a single product, but a portfolio of products that are operated under a single interface called Simcenter 3D Engineering Desktop. Using Simcenter 3D, you have access to virtually all the principal areas that structural and acoustics engineers need to work with. These could be structures, dynamics, durability, additive manufacturing, even such things as electromagnetics and composites. Today, we're going to be working in this area on acoustics. For a lot of people in the simulation world, they're working with siloed applications that don't talk to each other. There is no common model. There is no common interface. Training costs are high, and it's difficult for engineers to work across teams. Using Simcenter 3D, all of these capabilities are available in a single interface, and you can exchange information back and forth between the different Simcenter 3D products with ease because you are in the same product family. Here are all the things that Simcenter 3D can do. They can be structures, noise, vibration, and acoustics, thermal, flow, composites, additive manufacturing, motion and kinematics, rotor dynamics, both high frequency and low frequency electromagnetics, durability, factor of safety, and optimization, all within one product family. Today, of course, we're going to be talking about NVH and acoustics with a focus on acoustics for the space and aerospace industries. Before we move into the presentation itself, I also would like to point out that today's presentation includes references to acoustic testing and test data, as well as to acoustic simulation. ATA Engineering is the exclusive Siemens channel partner for Siemens test and measurement solutions. These include Simcenter Test Lab software and the SCADAS hardware. This is a complete solution for physical testing, not just for acoustics, but for many other areas. Acoustics is at the top of our list here, but you can also use Test Lab and SCADAS hardware for durability testing, environmental testing, TPA. We have a webinar coming up on transfer path analysis just next week. Model-based systems testing, rotating machinery testing, structural dynamics testing, and modal analysis for FEA model correlation. On the hardware side, the SCADAS line includes data acquisition systems from handheld units, not much larger than an iPad, to giant laboratory scale units that are designed to be permanently installed in wind tunnels and other major test facilities. If you have any interest at all in the testing hardware and software, please feel free to let us know. Now, I'd like to introduce today's guest speakers. Our first speaker is Dr. Korjan Kukakuskun from Siemens Digital Industries Software. He is an expert in aeroacoustics and will be doing the first part of the demonstrations and discussions today. Our second guest speaker, also from Siemens, is Dr. Bert van Genechten. Korjan, take it away.
Thank you very much, Scott, for the nice introduction. I will talk about the acoustic simulation and characterization in the aerospace industry using Simcenter 3D. And you already gave actually a brief introduction for Simcenter 3D capabilities, and we will just focus on the acoustics. But in case you have other questions, please feel free to ask also for Simcenter that we will also try to answer. We are looking for acoustics for aviation. It's mostly driven by customer comfort and regulation, of course, especially when it goes to the transition towards a sustainable aviation with low noise emission concepts. What we will present will be applicable to urban air mobility concepts, advanced air mobility problems, and also turbofan engine application, especially when it goes to in future where we have like electric powered engines, when the combustion noise getting lower and lower important. Aeroacoustics dominated noise will be also more important. So this technology can be also applicable for future hybrid engine properties. But what I like to highlight at the very beginning is that we are not going to talk about one single solver which can solve all these problems. We will show how the Simcenter portfolio can be used for different bits of the problem and how you can solve end-to-end your problem with different components of the solution. That's for the acoustics for aviation, as I mentioned, for comfort and regulations. But for space, it's not necessarily driven by the comfort and regulation. That's more an important problem also for the launch survivability, especially for the payload, such as antennas and solar panels, like structural panels, etc. They need to survive the existing external loads, which can come from the turbulent boundary layers or existing shock waves, and also gas exhaust from the engine during the launch. So it's another acoustics problem, but in a different perspective. At the end of especially for the second half, my colleague Bert will explain more about the acoustics environment. Today, we have a slide set for 3 case studies. We will start from let's say, lower applications with the drones, which is representative of urban air mobility problems. Then we'll continue with the aero engine intake noise and validation. And finally, we will go to the launcher for the lift of noise and also with the diffuse field acoustic analysis. All these three pillars are based on recent publications. In case you are interested, please reach us so we can also provide you more information about the publications and also link you to other experts. Let's start with the drone application. This is a problem that we work with the von Karman Institute for Fluid Dynamics in Belgium. And this work is published in ISMA conference in Belgium last year. The work is based on urban noise footprint of a multicopter drone. And we are looking for the acoustic field radiated by a drone towards, let's say, observers located in urban environments. What's the motivation for that? Because we are looking for an aeroacoustics problem for a drone, which is roughly speaking around like 60 centimeters in diameter, in size. But the exterior reflective surfaces like ground and buildings are a couple of orders of magnitude larger than this, right? So if you want to solve the problem for a drone radiating towards an observer in front of a building, you may want to split the problem into smaller chunks and then approach the problem in a way that it end-to-end solution can be achievable, and it can be even later used in, let's say, optimization cycles. So we are going to show how an acoustic field and equilibrium can be validated with free field assumptions for microphones nearby, but also we will show how the acoustic field around the building for observers close to the building will be computed. The goal is here that we don't want to solve the problem again for the flow, and we want to make sure that when we solve the radiating problem, we are not resolving the flow again for a building reflection. For the ones who are familiar with the aeroacoustic signature of a drone, you will see tonal and broadband components. This is a representative sound pressure level curve in frequency. You see the peaks, or sometimes tones. That's for the blade passage frequency and higher harmonics. They come based on the relationship between the number of blade and the rotation speed. And we know that due to the, let's say, perception of the human ear, this tonal content is the most annoying. So when tackling this problem, if you know that the tonal part is important and broadband can be negligible for that particular application, we can look for a solution which can solve only the tonal part. Of course, we have other applications where the broadband part is more dominant. There we can apply another formulation for this. But for this drone application, for also other urban air mobility problem, for tonal content is important, we can look for the formulation that will be presented in this paper. So again, for the ones who are familiar with the dominant noise source mechanisms for the propellers, you will see steady loading or thickness noise. But we know that from, let's say, let's say propeller applications, also with the in vicinity of airframe, steady loading might not be the most dominant one, but it may be important for an isolated propeller applications in free field. Also concerning the shape of the propellers, maybe the thickness noise is not important for this application. Therefore, we know that thanks to the installation effect of the airframe on the noise source generation, the unsteady loading sources will be the dominant one. This is also the showcase for this application. Therefore, we know that the loading noise will be the dominant contribution for the subsonic applications. You can approach to this problem with different simulation techniques. You can do high order techniques too, but they will be more expensive for just for the tonal fan noise problem for this urban air mobility application. So therefore, they may not be suitable for industrial design of optimization cycles. Of course, they will give you accurate results, but it may be in higher cost. So what we are looking for is reducing the cost for the end-to-end problem. Therefore, we look for a trade-off between the accuracy and computational cost. And since we know which frequencies that we are looking for, and we are not interested in the broadband component, we can solve the problem with what we call it unsteady run simulation. So that will give us the unsteady aerodynamic forces on the blade. This will be exported from the flow solution, and then we will use a fan-based acoustic solution to compute the near-field acoustic application in an equilibrium to get the observer levels. So the application is a quadcopter. Two of the propellers rotate clockwise, the other two rotate counterclockwise, and this a representative of the flow domain. I will not go too much into details for the computational cost and modeling. You can find information in the paper for the application. But what I can tell that this is a k-omega SSD model, 3D solution, not 2D or cycle-symmetry. We are looking for ideal gas model with 6,000 RPM propeller. All propellers rotate in the same RPM in different directions. And the time step of choose was like 8.3, 10 to the power of -5 seconds, corresponding to 3 degrees of rotation. And once the simulation is performed in Simcenter StarCCM Plus, in this case, that the authors validate this with, let's say, 1.4% accuracy with experimental thrust. This is very important for any aeroacoustics problem because we need to first make sure that aerodynamics is well captured such that we can use those aerodynamic fields to create a noise source. And there you can actually find more information on a recent paper in the Journal of Aerospace Science and Technology published last year on all this exercise. Our users in Fermat Institute also did exercise to see how much the airframe is affecting the aerodynamic source generation, also how much the airframe also affects for the propagation. So you will see in some interested outcome also for this publication. I will not show too many formulas here for the presentation, but what I can show in a nutshell that we are using a typical Foxley-Hawkins analogy. And since we know this is, let's say, a subsonic and thin blade applications, some of the terms can be neglected. We are not saying that they are not there. We say that could be negligible. So we can drop this problem as simple loading noise application. And then the exporting only the surface pressure on the blades, we can create an equivalent noise source in Simcenter 3D. This can also use the airframe as a scattering surface, and then it will give you like directivity changes in the immediate neighborhood of the quadcopter. You can see a sketch of a cut plane of the mesh used in Simcenter 3D. You see it's a convex mesh, and which the convex boundary has two properties. One, it doesn't let acoustic waves generated by the source back in the finite element domain, but also they let acoustic waves propagate freely to the far field observer. So you don't need to mesh, obviously, all the acoustic field all the way towards an observer. So observers can be outside of the FEM domain. What I like to highlight here is that for the ones who are familiar with FEM, this may not be the best mesh because there's not a uniform mesh distribution. Some part is fine, some part is coarse. Because we are using a finite element adaptive order terminology here. This is based on refinement of the acoustic mesh and using high order shape functions. Just to give an example, for the ones who are familiar with finite element concept, you need to mesh your problem with, let's say, a rule of thumb, 6 elements per wavelength. So if you are solving multi-frequency problem, let's say multi-blade passage frequency, you need to create a finite element mesh which is accurate for your highest frequency. So then you will solve different frequencies using the same mesh, and suddenly you will use very fine mesh for a very low frequency. You see here a basic sketch representative of a coarse mesh. You see that the mesh gradually gets bigger and bigger. And for a standard FEM, this problem cannot be solved at 100 Hertz because the rightmost mesh element is very large. You need to cut it into 2 at least to make sure this can be supporting the 6 elements per relay. But for FEM adaptive order, that's not a problem because we can increase the element order in the solution, in the solver in the background automatically. So this will put the element order 3 and introduce the new shape function and then solve the problem for high frequency. And it's not only for 100 Hertz. This is the same mesh which cannot be solved with standard FEM at 100 Hertz, can be solved in finite element even up to 1000 or so, 10 times higher the frequency. So you don't need to worry about creating fine mesh for high frequencies. This will be taken care of by FEM adaptive order. So you will see different meshes, especially in the center of the cavities. You can use very large elements. Of course, you can have like smaller elements represent your geometry for curvature, but for the center of the acoustic domain, you can have very large elements. This is the benefit of finite element adaptive order. We will use finite element adaptive order for the near field, and using that, the validation can be found also in the paper that for the first 4 BPF, we got very good agreement between the measurements performed in anechoic room together with the finite element model used in Simcenter 3D. So the delta dB is around 3.5 dB and acceptable for the first 4 blade passage frequency. So this already validates now for free field anechoic room performance. but let's go next step to put the drone in a hovering position in front of a building. For this, we are adding a new solver on top of existing finite element framework. This time we are using array application to tackle acoustic propagation using Simcented array acoustics. So it is based on ICAR solver from CSTB, and this simplifies the problem for a high Helmholtz number problem. It includes adaptive beam tracing or smooth surface description together with high order diffraction. You can see it in the animation, for example, what happens if you have a noise source shown here and a reflective surface here and also the wall. So when the acoustic pulse comes towards the observer, if you don't have smooth surface, it will be cut into smaller chunks. This is not the reality. In reality, you have smooth surfaces. That's more taken care in the solver as smooth surfaces. And finally, you can add the diffraction to make sure that acoustic waves actually follow the pattern. I will let the animation run once more so you can see the differences on adding more physics on the propagation. So here we used also the 2D and 3D diffraction for the next section of the presentation to show how accurate it could be captured. And here we are looking for representing a finite element problem in a way that we can transfer the information to array application. Therefore, we benefit from source directivity here. We create first the acoustic field around the sphere in free field of the drone using finite element application. And then this goes to ray model as a point source with directionality. So this sphere eventually shrinks back to the drone position as a point source, but getting full 360-degree directivity. And that's done in the Simcented also using a directionality application. And once you do that, you can position this drone anywhere in the space and to be able to get the reflection from external boundaries. For example, this is the library building in Leuven, and then we put 3 hovering points to show the real part of the pressure. You see the reflection, and you also see the interference fringes and effect of the gallery. Of course, you can tell that these are just colorful images. We can look for some validations. We don't have experimental validation for that, but we can actually mimic, let's say, large domain reflection with analytical models. For example, this is the free field representation of a drone located in point S. And here we are not taking into account any reflection, no ground, no building, nothing. But what if we just add a rigid ground and ignore the building? So with ray acoustics, we can add the ground and then solve the ray problem. And then you see the interface fringes. This is again the amplitude of the pressure that you can see the pattern. But also, since this is infinitely large ground, you can actually put a mirror source to represent the analytical solution. So here, instead of one source, there's another mirror source here, and then this gives actually the same results as ray problem. On top of that, we can add the full building as a reflective surface and assume in the analytical model, full building is infinitely large. So then we can actually now mimic the mirror problem. Instead of one drone, we can put 4 mirror drones, and then the total contribution will give us the total response. And in ray, we can do the same, and we will get actually accurate representation of the propagation. You see that especially close to the flat surfaces, the results are similar, but ray is more accurate close to the gallery entries because it is based on unrealistic geometry and it's not just image source. So this actually validates, let's say, qualitatively that these two application can give accurate results and ray can take into account more geometrical details of the propagation. One last thing to show that is the diffraction FX. For example, if you have an observer located on the side of the building and for a drone operating in front of the hovering in front of the library, you can see the acoustic field is split into 3 dominant regions. First one is the total field, which includes the incident field plus the reflection from the wall. Second field is the triangle area here, which only includes the free field response and without any diffraction, because here we ignore the diffraction. And the 3 is the perfect shadow zone. The incident field doesn't reach it because the direct ray is cut by the building. You don't see perfect 0 here. You have some acoustic field because there are like openings under the gallery. So some acoustic rays goes to under the gallery, reflect back and create some levels. But to be represented more accurately, you can define that this edge of the library is diffracted, and then you can see the continuous, let's say, distribution of the three acoustic domains. Again, the total field, incident field with the diffraction, and also the shadow zone with diffraction. But of course, now they're all total field eventually. And you can also plot the ray paths to see how the acoustic waves reach to an observer. That could be interesting if you have multiple diffractions, and you can follow where the observer is located, and you can see how acoustic waves reach. And you can also do echograms that are not shown in this publication. So that is, in a summary, how a drone operating in an urban environment, and the application is based on coupling different solvers where you don't need to resolve the flow again if you change the reflective geometry. Of course, this is based on assumption that the building doesn't change the flow, and this is a one-way coupling. Okay, so that is for the drone application. I'll continue now with the Aero Engine intake part. This is based on a publication of my colleagues, Sylvain and René. They published their work in earlier this year in ASME Turbo Expo in June. The work is about integrated CFD and a finite element acoustics workflow, focusing on the tonal fan noise and with validation with experimental data available in literature. So if you're interested, I can also link you my colleagues, and I can also provide more information about this recent publication. Similar to the drone one, if we look at the acoustic field generated by the turbo engine intake, that you will see the fan and outlet guide wire configuration give, again, a tonal response. You see a broadband component, but you see that sharper tones, and they are like spread on the higher frequencies in general because of the higher RPM compared to drone and higher blade count. You also see individual pure tones, but they are not the concern of this study. We are now looking again the sharp tones and then approach this problem with, let's say, a similar hybrid solution, solving first flow and coupling with acoustics. My colleagues use the data available in literature based on the NASA Advanced Noise Control Fan, ANCF. It is based on a low-speed ducted fan, and that's also in the measurements are available for the far-field microphones. My colleagues, and I also thank you all, Dr. Daniel Stutliff from NASA Glenn Research Center for providing for the geometry for ANCF and of course the relative experimental database. And using this model, we create a representative sketch for ANCF test bed in Simcenter. You can find more details on the test model in the paper. I will not give too much to this. It's a representative application with a scaled RPM. But overall, you have like 16 blade and 14 vane count. And we are looking for measurements available on the two microphone arcs, one located in the forward and the other one is the backward fan. And like you can say upstream and downstream end of the fan. And we will compare the simulation results with measurements on these arcs in this study. I mentioned about the previous drone study that was using U-runs, and since it was also an open rotor, and we were looking for the tonal case. But here, it is a ducted propeller. It's not free, let's say, isolated component, but it is also rotor-stator interaction application. And this also made our colleagues to change the direction a bit and then look for a different flow simulation calculation. This time, they are not using U-runs, but they are using runs coupled with harmonic balance method. So harmonic balance solves a slice of the problem, let's say a sector of rotor-stator model, which I will show in the next slide. And then that creates an equivalent noise source. And then using that, they use FEMEO technology again, as I mentioned, and that could give us the acoustic field radiated to outside of the, let's say, the Aero Engine intake and exhaust. What is interesting here is that they are both based on same CAD model. So this is also aligned to what Scott mentioned at the beginning, that the source of truth is the same CAD. So you can create the CFD mesh also based on same CAD. Also, like the acoustic mesh can be created on the same CAD data. What I want to mention here, the data transfer from harmonic balance and FEMEO is based on, again, CGNS files, similar to what we did for the drone. But this time, this is scripted. So my colleagues work on the harmonic balance output file, fill it in a way that they convert it to a time signal that can mimic the equivalent CGNS input for the FEMEO problem. So this is also shows openness of the software for user-defined input and to be able to create user-defined noise sources also, or at least let's say pressure distribution outside of Simcenter 3D. And using the CGNS data, we create again noise sources. You will find more information in the paper too. And again, please feel free to reach us out that I can also share more information on this if you're interested with the harmonic balance solution. So we are looking for a rotor stator sector using Simcenter Stat CCM Plus. Again, an ideal gas application with Spalar Almaraz with sure conversion, curvature correction. And that will be used also as an input as a noise source. So this is for the flow part. Again, we are not solving the acoustics necessarily here on this application in harmonic balance. We just extract what we want as a noise source for the downstream simulation for acoustics. So this could be also considered as two-persona workflow, where one team can work on the flow and then give the loads to an acoustics team, and acoustic team take care of the acoustic propagation with the input from another team. This is a simple representation of the Simcenter 3D model. You see a convex mesh around the aero engine model for the NCF model. We have the microphone arcs, both upstream and downstream. And finally, we had a cut plane of the 2D microphone mesh. Of course, for validation, we don't need the 2D microphone mesh, but we want to also show how the acoustic waves propagate on both sides and not necessarily stick only on the directivity curves. If you look at a close cut plane of the full domain 3D mesh, you can see that we are using actually very, very coarse elements on the curvature, also for the, let's say, the what we call automatically matched layer surface, which can radiate acoustic field outside. And for a high frequency problem, the regular FEM models can consider this as too coarse, but FEMEO can take care of these large models with, let's say, high order elements. And using the sources again with both on the rotating component, but also this time on the stationary component. So for this is water fan noise coupled with the, let's say, vane noise. My colleagues computed for 3 blade passage frequency BPL1 in the left, BPL2 in the middle, and BPL3 on the right. And they first on the bottom, you can see the, let's say, the propagation towards far field microphones. This already gives an insight. You see the directivity and also the interference fringes due to two noise propagating direction canceling each other in the middle. But this is also visible in the microphone arc. So here in this case, x-axis is not frequency, but the polar angle, and the y-axis is the sound pressure level in terms of decibels. And there are 2 experiments available in literature from 2008 and 2018. And the green curves are the harmonic balance and FEM adaptive order solution. You see for both 1, 2, 3 BPFs, there's a very fair agreement between the experiments and measurements. For some of the observers, they are a little bit different than let's say the propagation. This could be related to measurement artifacts or modeling problems, but overall, this gives us, let's say, a good estimation of, let's say, the acoustic field generated by the aero engine and propagation from both inlet and outlet. Here, the noise source is not the combustion, but it is more the aeroacoustic component, and this radiates towards the far field observers. If I go back to the FEM adaptive order and order distribution, what I like to show you, now we computed 3 blade passage frequency in the same mesh, but solver also gives you actually an indication of how the acoustic orders are distributed for high order elements. So you see, using the very, very same mesh, you can get, let's say, for the third BPF, which is a higher frequency, it has more orders of high order elements. And if you go to lower frequencies, like second and first BPF, you will have less element order. What happens, what this doesn't give us maybe too much information, but what I can highlight here, using the very same mesh, high frequencies will start to solve, but then once they solve, the lower frequencies will solve much more faster compared to the higher frequencies. So your solution will increase. Let's say the time spent per frequency will decrease with increasing, let's say, the frequency marching. So the high frequency will be more expensive to solve, but using the very same mesh, the low frequency will solve faster. But if you need to solve this with standard FEM, of course, then every frequency will probably solve same time, and it will be computationally more expensive. finally, that is for the, let's say, the rigid wall aero engine, but luckily aero engine, let's say, applications let us also define liner surfaces before the acoustic field leaves the duct. And you can see that here for the liner application, and you can do a rigid wall or liner treatment here to apply acoustic absorption. We also take into account Myers correction. You can also include the flow effect. And then finally, your directivity will be lower. Also, your sound pressure level will be lower because we can absorb some of the acoustic energy. And especially for the ones who are designing liners, a 3D model can be also helpful on top of the, let's say, the axisymmetry, let's say, studies. So this gives us an insight on how acoustic treatment can be applicable for aero engine intake problem. But once we know the source modeling, as I mentioned again, which actually this part is not in the paper, you can also link it for other propagation tools too. So we show here harmonic balance coupled with fan adaptive order. It could be based on fan source, or you can also script it to get the duct modes. But you can also link this solution to another band problem where you can also get the acoustic field outside of an aircraft, together with the reflection from the aircraft engine, to see how the acoustic waves generated by the intake are reflected and scattered by the aircraft body itself. So this can also give you an idea. That could be also interesting for ramp noise applications. In case this engine also initially starts, you see how it radiates. Of course, for ramp noise, you also have APU and other noise sources, but that can be also tackled with similar application. And as described also in the drone application, you can also put the ray model and then solve the acoustic problem. And it's not only source characterization, but also for the install and propagation with urban environment. Okay, so this brings me end of my part. I will pass the slides to my colleague Bert, and then he will continue with the launcher and the fan application.
Okay, thank you very much, Korcan. So this indeed brings us from the aerospace domain to the pure space domain with launcher liftoff noise and DFAN. So the use case we've selected here as the final use case to present is the acoustic characterization of, on the one hand, the liftoff acoustic loading. And for this, we will also use ray acoustics because of the sheer size of the problem domain we're faced with. Here you can see, for example, the Vega C launchpad. And then on the other hand, we're also focusing on digital twins, which can help us in direct field acoustic noise testing. So this brings us a little bit back to the testing activity that Scott referred to in his introduction. And we will show how these new types of qualification testing strategies can also be supported through simulation. So going back a little bit to what Korcan mentioned before, going from aerospace, where it's more comfort and regulation, to space launch, it's more structural integrity, launch survivability. So there are extreme acoustic loads which are generated during liftoff, and we ideally want to characterize those and then also confirm that these launch levels and characteristics will not damage the very sensitive and very expensive equipment which is typically being launched. For that, there are a lot of simulation challenges. And the first one that we want to highlight is actually the need to characterize the pressure fields at the exterior of the fairing and then also the propagation to the interior. We know that the levels are high, but are the levels uniform? Are they diffuse? And typically, they are assumed to be diffuse and uniform. So basically, traditionally, acoustic tests on spacecraft are performed in large reverberant rooms. But we also know from some of the tests, due to the asymmetry of the surrounding of the launch vehicle, for example, you have basically the support structure and potentially other buildings in the vicinity, which may divert some of the acoustic energy from the exhaust plume towards the rocket. There might be an asymmetry in there. And that's why a lot of research effort is put into developing new testing methods. And one of those, which is getting more and more acceptance in the qualification area, is direct field acoustic noise testing, where we place large stacks of microphones such as shown here in this picture, and I will come back to this use case later on. They are placed around the test specimen, and then advanced multi-input, multi-output acoustic controls, as the ones available in the Simcenter Test Lab environmental testing suite, are used to actually generate either equivalent reverberant loads, or could potentially even be used to generate these asymmetric, more realistic loads. Let's first start with this first challenge, the launch environment simulation. And for those of you who want to get a bit more technical details than what I will present here, actually, at this moment, this week, some of our colleagues are presenting the work that I will discuss now in the next slides during the Forum Acousticum conference, which is being held currently in Turin in Italy. So it's focusing on acoustic characterization of the Vega liftoff environment. And for this, we are using ray acoustics modeling. And then we're also linking this to direct field acoustic noise testing. Now, as I said, one of the primary launch environment loads are the loads from the exhaust plume. So what we need is, one, a simulation model that can predict the environmental propagation of acoustic noise due to the exhaust plume, and we need a source model. And for this source model, we're actually using a well-accepted analytical equivalent model, which was developed by NASA, which is basically the distributed source method, where we can actually excite the model acoustically by representing the plume noise sources as a discrete set of individual point sources with some semi-empirical determined fractional engine power contribution for each of the sources, which depends on how far along this deflected plume source path the source is positioned. So basically, we can use these type of source distributions, and we can actually introduce them in an environmental model where you can here see basically the Vega launchpad geometry, which is being reproduced or represented in our Simcenter 3D environment, where we have the launcher, we have the launch tower, we have large buildings in the vicinity, and we also basically have the launch plume deflectors, which are modeled, whose geometry is modeled in detail below. We then basically introduce this distributed source method model, where you can see each of the individual red dots represents a source contributing to this acoustic loading, which we will then basically apply to this model with the aim to predict actually the block pressure loading on the launcher, and especially the fairing at the top. As Kortjan already mentioned, our ray acoustics solution is a very attractive solution for this because it is specifically tailored at high frequency applications for very large environments, which leads to large Helmholtz numbers, which means that we can use ray tracing models. Additionally, as Kortjan showed, we have very advanced physics included. For example, higher order diffraction models, which you can see here. Actually, so what happens is that the noise contribution from one of those sources, it bounces off the deflector, but then actually in reality, it bends around these sharp corners of the supporting pad on which the rocket is positioned. If we wouldn't have these high order diffraction models, we would not be able to capture this deflection, and we would misrepresent the distribution of the acoustic energy. But as you can see from this acoustic path, we take it into account, bounces off the launcher, off the launch tower, and then again towards the fairing. With these models, we can actually quite efficiently capture all wave reflections, and we can then also predict the noise levels both near the ground surface, near the deflector area, but also at the fairing. Now, for experimental validation, it's quite hard to get reliable data because it's a very difficult environment to measure in. What we did find back is we can do a qualitative estimation where we see that from this publication, specifically on the Vega Launchpad from 2016, there is a statement that the overall acoustic levels from the plume of the advanced solid rocket are estimated to be higher than 180 dB. And this is also the range of levels that we find back from our simulations. So once we have this distribution, you can see here at different rings around the fairing, we can see a clearly asymmetric loading due to the reflections of the buildings in the vicinity. Then, of course, the question is, can we now reproduce this, and which type of testing environment can actually do this? And this is where direct field acoustic noise testing comes into play. So like I mentioned before, it's a rather recent testing strategy, which offers an alternative to reverberant room testing, where we actually position a large number of typically commercially available loudspeakers, for example, the loudspeakers you would use at a rock concert. We drive them with a multi-input, multi-output control system in such a way that we try to reproduce the desired acoustic environment around the test specimen. Now, most of the research has been focusing on generating diffuse acoustic fields equivalent to the reverberant room fields in order to be able to have a one-on-one comparison between those two testing methods. And that's also what I will be discussing now. And if you're interested in both our testing methods, but also using digital twins, so digital counterparts, representations of such test setups, and they're used to do pre-testing and de-risking of tests, I can refer you to this journal publication of which came out earlier this year, which discussed in detail the technical background. And we also have a publication on a parametric analysis, which was presented in May this year at the 33rd Aerospace testing seminar. So basically, a little bit of background information on direct field acoustic noise testing, because this is actually a simulation activity which supports and enriches, facilitates testing with environmental testing systems like the ones available in the Simcenter test lab environmental testing. So basically the question is it possible to reproduce acoustic environments around the fairing in the laboratory? The classical answer is use a reverberant room test. It's a standard practice since decades. So basically very large rooms are excited by huge horns, which allow to reach a diffuse field condition around a test specimen with very high sound pressure levels. Sound pressure levels similar to what the test specimen will see during launch. The alternative approach, which I will be focusing on now, is direct field acoustic noise testing. It's a cheaper and more flexible approach because actually you bring the testing facility to your specimen. You build this tower or this cylinder of loudspeakers around your test specimen. For example, here, it's a reflector dish. And then you use basically a multi-input, multi-output closed loop control strategy to shape the acoustic fields around the specimen such that they match the field that you want. It's a very active field of research. There's a continuous improvement of technology. And this activity with using simulation models to support this is one of those activities. So basically, the way that the MIMO controls works is the speaker stacks are linked to a control system, which drives individual speaker types or individual speaker stacks, speaker stackings individually. And basically, it's typically we apply a narrow band multi-input, multi-output control, which is basically designing random signals to drive each of the individual speakers or speaker stacks. It's a closed loop system. So basically, there are some microphones positioned in the inside volume, which are then used to iteratively or online change those random signals such that we basically reach the correct levels and the correct acoustic fields. It's based on conversion of the specifications that we typically get in SPLs from the launch authorities documents, specification documents, and it's converted to PSD. And then basically the system generates a spectral density matrix for the targets, both in amplitude, phase, and coherence. And then what is recommended here is a pre-test analysis. So basically doing a virtual test upfront, such that you know how the system will react, that you know how the system will interact with the specimen, such that you can already foresee potential issues, and you can also correctly design your test setup, which speakers to use, where to position them, and how to connect them to the different controls outputs. On top of that, you can also automatically select the best location for the control microphones. Typically, you only have, for example, 8 control microphones. Where do you position them? You can use experience, but depending on the test specimen you're working with or the specific test system configuration, this might be different. So the challenge here is, can we improve the test design and make it more efficient using a simulation tool? So we know we're going to test like this, but we only have a limited number of sensors, and it only gives us a partial view of what's going on during the test. And can we predict actually upfront some unwanted effects, like, for example, standing acoustic waves between these different stacks of the speaker, or, for example, between the speaker stack and the ceiling of the room, or vibroacoustic couplings. And the solution that our research team worked on was actually to estimate the full system response using a simulation model, which really mimics all the components of a defense setup. And in that way, you can have actually a high fidelity model, which complements your testing and which allows you upfront to assess how the system will behave, how it will interact with the specimen, and how to optimally choose all your parameters and all your sensing locations. So it allows you to optimize and de-risk your test setup, basically on your laptop. It allows you to predict vibroacoustic response of the specimens and on-site estimation of pressure levels and structural response in unmonitored locations. So the system looks broadly like this. So these are the different components. You have a control and signal generator. For that, we typically use our Simcenter SCADA systems. These send out a low voltage system, which is sent through digital audio processor to reach a high voltage input to the speakers. So we have the speakers themselves. They generate a membrane velocity, which then basically transmits noise into the testing volume, and that hits the structure and the different microphones. So I'll take you through the different components. I'll leave out the SCADA system because that's basically controls hardware. Let's basically start at the digital audio processing system. For that, typically, we have quite well-known measured frequency characteristics. So this is basically the output voltage over the input voltage as a function of frequency, in blue for a low frequency speaker. For the mid-frequency speaker, you see it in yellow. And so basically, you can have this for different types of drivers. You can actually characterize this experimentally. Then the voltage enters the speaker. How to deal with this? Well, for that, you can actually develop dedicated loudspeaker models, which are based on electromechanical equivalents. And you can actually introduce these as source models in an acoustic radiation model. So basically, you can model the speaker box like it is here. So this is a vented speaker box where you have 2 diaphragms. You can introduce these equivalent loudspeaker models. You can model very similar to what we did with the drone before. You can model the acoustic environment and the radiation around it. And you can then basically predict what will be the loudspeaker membrane vibration. And here you see a comparison between in blue a test and in red the model, which shows a very nice agreement. Of course, this then needs to radiate towards the acoustic environment. So with that exactly same model, we can actually calculate what is the sound pressure, which is being radiated. And here you can actually see a comparison between in blue measured sound pressure level over control voltage or input voltage. In blue, we have the test, and in red, we have the simulation, which also shows a very nice agreement. So once we have these components, we can start building stacks of speakers. We can introduce voltage inputs. We have the DAP characteristics, and we can actually build a digital twin. And this is also where the one of the key strengths of this integrated simulation platform comes into play. It allows for a high level of process automation and customization. So we can basically easily and quickly model a setup via a parametric CAD creation, where we actually can parametrically change the configuration of the loudspeaker stacks. We can then automatically mesh this for the acoustics, also taking into account actually the coupling to the specimen which will be inside. And we can then actually create one vibroacoustic model, which we can solve with Simcenter Nastran for both the acoustic and structural responses. And it also has the openness to allow you to introduce MIMO control strategies and pre-testing through scripting. And we can then have dedicated post-processing, which we can implement, for example, here looking at acoustic pressure inside the testing volume, or as you showed before, the structural vibrations. And we can even build custom dashboards, which mimic your testing application, which I will show later on. One small, let's say, quick validation case I want to discuss with you. We actually made this extensive digital twin of a DFAN testing campaign, which was conducted in 2017 at Thales Alenia Space in Toulouse with an antenna reflector as test specimen. So here you see the test setup, courtesy of Thales. And just some information on the test. There were actually 96 speakers used. So 10 three-way cabinets, like the one you showed, 6 times 10 three-way cabinets, as you've seen before, and also 6 times 6 subwoofers, which were positioned around the specimen. There were 6 drives, so by column, 1 for the top, 1 for the sub. There is the inner radius of the testing volume was 2.6 meters. There were 30 microphones. There were actually 16 candidates for control. Like I mentioned before, typically you use like 8 control microphones. Here we put 16 at likely locations, such that we could check if we only take 8 out of the 16, how well is the control, etc. So it was also more a research activity. And there were 14 placed in front of the antenna, such that we could monitor what the sound field looks like that's hitting the antenna. And then there were 13 accelerometers placed on the rear face of the antenna. We went up to 10 kilohertz testing. And basically, we built this digital twin of the setup. So we had a vibroacoustic model with the same frequencies. And then we also included the finite model of the antenna. I quickly want to take you through a few results just to show you how well this digital twin can capture such a complicated test. And for the first one, we actually simulated driving all the speakers using uncorrelated input signals. So we include the cabling, the way that the different drivers are linked together, and we put uncorrelated input signals to it. And we look at the microphone, which is positioned here in the testing volume. And on the right, you can see the very good agreement between the test in blue and the simulation in red. At the same time, we also simulated the transfer functions when we drive only one of these input drive signals with a unit voltage, and we look at the acceleration on the antenna, and we can actually see that we capture very well both the vibration levels, but also the phase information. We have a very good prediction agreement there, and with those models, we can now actually predict what happens in the test. And for that, we can then also virtually run this test and do what we call a pre-test. So we basically process the targets, we enhance the reference profiles, we optimize the performance indicators, we can check the voltage requirements, and we can then also check which locations are optimal for using as observation sensors. And we can then, actually what our team did was through scripting and with the openness of the platform, they built this dashboard, which reflects very well the dashboard that we have in our test lab application, such that we can do a similar analysis that you would typically take days of pre-testing to do. We did it basically on a laptop up front. The result we got was, if we were using the best practice common sense approach to place the control microphones, we would get, for all the observation microphones, all the dashed lines as responses. The green curve was actually the target we were trying to reach, and the allowed tolerance levels were the dashed blue and dashed green line. The red line should no way be crossed because that would damage the specimen. We see here that 94 bands are out of tolerance, even though we're using experience with these kind of tests to place them. If we do the virtual pretest analysis, we narrow down the uniformity of the field, and we only have 5 bands which are out of tolerance. And this shows actually the strength of using the automation and customization capabilities we have inside Simcented 3D, together with the high fidelity vibroacoustic simulation technology and science. This brings me at the end of the third application. So I hope this was very interesting for you. We showed you 3 actually quite different but very relevant applications in the aerospace and space domain, going from drone noise in urban environments, where we both considered free field radiation, including experimental validation, and plugging it into an actual city environment. We have the aero engine intake noise, both with experimental validation and the capabilities of liner optimization, and then launcher liftoff noise and DFAN digital twin, where we can actually de-risk and enrich our testing through high fidelity simulation. I thank you for your attention, and I will pass it on now again to Scott for the Q&A session.
Thank you very much, Bert. I am going to apologize that we are at the end of our hour, so I'm only going to pass on the 3 questions that came through the chat. The first question is for you, Bert. It says, for the DFAN simulation, is this part of the standard Simcenter 3D product portfolio?
That's a very good question. As I mentioned in my presentation as well, it's actually not part of, it's a very interesting application, but it's not a standard product. Because what our research team did here, actually, they had a need for vibroacoustic prediction on this very challenging DFAN type of setup. And they actually used the openness and the automation of Simcenter 3D to build an application which fits their needs. So it's very much a research activity, but it shows very nicely the capabilities of combining scripting for the controllers, customized layouts, and automatically driving solvers to build a very nice integrated application for your hands.
Very good, thank you. And the other 2 would seem to be more likely for Korjun. For the FEM adaptive order modeling, can we use very large elements on the surface of the acoustic volume also?
Yeah, that's correct. Depending on the application, Scott, if you have, like, for example, a flat plate or exterior domains, yes, we can do that. We also do high order coupling when there's a structure. But in case we have geometrical details, there the geometry itself forces you to create, let's say, finer elements to represent the curvature and geometrical detail. But if you're not concerned with that part, yes, you can use very coarse elements.
Very good. And the last question for today is, when linking the FEA results with ray sources, can we select the sphere microphone radius randomly?
Yes, it's not random, of course, because what we do here is creating an equivalent source using directionality and based on pressure. So we need to make sure that acoustic field is captured on acoustic far field. So we need to make sure that this 1 or 2 wavelength for the frequency of interest needs to be there in the radius, and then you can capture it. Actually, the paper itself refers an exercise of that, how you can make mistake there or how you can get accurate representation. So I'm happy to support in case more technical details needed for this question.
Very good. Thank you so much. I want to thank our speakers today for the excellent material that we showed. Thank you to all of our participants. Thank you for joining us today. If you have any questions or would like further information on Simcenter 3D or Simcenter 3D Acoustics specifically, please contact me. My information is shown on the screen. Thank you for joining us this afternoon for this ATA educational webinar on Simcenter 3D acoustics for the aerospace industry. Thank you very much for joining us.